Hello, we are called the Cooked Cerebrals. Our group members are Jason, Hansel, and Arjun. That's myself. This is our final project talk for the Cogs189 final project. So, we've learned a lot about brain-computer interfaces in this course, and our project aims to demonstrate some of the key concepts that we've attempted to put into practice. For some context, modern games require many physical inputs to play nowadays, such as mouse and keyboard. And for those who can't easily use these tools, many BCI systems have been explored as alternatives. In our project, we want to analyze and explore how feasible it actually is to be able to perform complex tasks using an SSVP system. And our problem is important because it will allow us to learn both about the effectiveness of SSVP and its limitations. So our primary goal in this project is to explore BCIs in practice. So we took a game that we were all pretty familiar with, Hollow Knight, and attempted to incorporate an SSVP-based control system into it. We wanted to see if it was possible to actually play the game and fight a boss using BCIs in our project. So Hollow Knight is actually a pretty complex game that requires the user to make quick decisions and press or hold down multiple keys at once. For an SSVP-based system, this can be quite complex to manage, so it'll serve as a good benchmark for the possibility of applying BCI systems to other complex scenarios. So, to summarize, we want to explore the possibility of using SSVPs in complex real-time scenarios, and we'll do this by applying our process to Hollow Knight. Not only will we gain experience working with BCIs, we can also learn about the strengths and weaknesses of SSVPs in the real world. We were interested in SSVPs because of their ease of use and training, being fairly simple for subjects to use for data collection, and for users to interact with in general. This is what most of our project focuses on. We also decided later to incorporate eye-blinks into our model as well, as a method of confirming inputs, since they are also easy to use and produce consistent artifacts in EEG data. And then, of course, all these signals require preprocessing in the form of signal filtering, and feature extraction to boost classification, as we've discussed in class. Here we have a publication on a prototype SSVP-based real-time BCI gaming system that seeks to answer a similar question as ours. Can EEG-based BCIs function as real-time game controllers using SSVP? In this study, the research team answers this question by testing out a couple different models and feature extraction methods to play a simple target shooter. They discuss EEG-based BCI architecture, going from recording to preprocessing to feature extraction to classification, plus potential limitations of EEG controllers such as their reliability or transfer rate or general ease of use. This is closely aligned with our project, which addresses how we could approach making a real-time SSVP controller for a more complex game. This study used a 3-class SSVP setup for left, right, and center movement, plus an additional class for no input or control. They gathered 4 EEG sessions, collecting data from 2 subjects with each session including 20 trials per class. They tried multiple feature extracting techniques combined with different classifiers, and ultimately achieved 80.5% accuracy with SVM, and concluded that BCI can be used as an interaction technique for complex applications, providing real-time operation and feedback. This paper was a good starting point for us. We aimed to push this further by incorporating more classes to map to the required available actions, incorporating eye-blink detection in our controller to use as confirmation of input commands, and by customizing the layout of our SSVP interface to ensure gameplay compatibility.
So let's quickly break down what Hollow Knight actually is. Hollow Knight is a 2D platformer game that requires the user to jump around and attack enemies. It's meant to be challenging and requires a lot of practice to master. The goal that we set for ourselves is to be able to challenge and defeat the first boss, known as the Groose Mother. For our task, we only need 8 different input controls to successfully play the game. One challenging aspect of the project comes from the fact that in the game, the user will often want to press multiple keys at once, and often hold down keys for specific amounts of times as well. Initially, we wanted to explore motor imagery in addition to SSVPs. We wanted to use SSVPs to control player movement and handle discrete actions such as attacking, jumping, or even dashing using motor imagery. However, we decided in the end that it would be quite challenging to gather good data, due to both time constraints and the fact that motor imagery data can be difficult to detect. Instead, we switched to using eye blinks instead of motor imagery. We decided that it would be easier for the user to select an action using SSVP, then confirm their selected action using a double blink. To actually get our SSVP running, we started with the example of speller code that we used in the lab, and we thought it would be really simple to implement it. However, we realized it would be somewhat hard to get the user to focus on both the SSVP and the game at the same time. Another challenging aspect that we had to consider was gameplay itself. We realized that we can't have the user attempt to play the game live, since it took a second or two for a user to select an action from the SSVP. As such, we automatically pause the game whenever the user needs to choose an action, and unpause the game once they've made their choice. So our final SSV design includes 8 flashing squares that surround an empty space in the center. We only needed 8 different stimuli squares for our actions, allowing us to increase the frequency difference between each square, which would allow for more separability in the different EEG signals in our data, allowing for more consistent classification of the algorithm. The game is then paused while the user selects an action. After the user chooses what they want to do, the game is unpaused for a length of time, calibrated to how long this action would take. The user can actually select 2 actions at once, since a large part of the game is about doing multiple things at once, like attacking in a certain direction. Our final control system allows the user to choose one action, then either double blink to confirm the action, or wait a second or two, allowing them to choose a second action that will be executed in sequence. When we collected training data for our SSVP, we did 32 trials per session. This allowed us to get 4 different trials per possible label, and we had 8 labels corresponding to 8 actions for the user. In each lab session, we typically trained the data to be around 8 to 10 total sessions. Finally, the channels themselves are shown here. Generally, O1 and O2 are the most important channels for SSVP, while FP1 and FP2 are the channels that we use for eye blink detection.
Once we had our data, we needed to be able to map detected signals to specific action labels. To do this, we explored 2 different classification algorithms. We initially looked at CCA, or Canonical Correlation Analysis, which is a commonly used algorithm for SSVEP data as a baseline. Our final result uses FPTRCA, which we adapted from Simon's Stark lab code, and we found better results using it. To expand on CCA, it's an algorithm that works with no training data, so it would serve as a good baseline. In our implementation, we first generate some reference signals for each of our 8 labels that we match with a predicted theoretical signal. Then we provide our EEG data as an input, and the CCA algorithm from sklearn finds optimal weights that maximize the correlation between the input data and the ideal reference signals, predicting the corresponding action label. When CCA was applied to our initial train data from 9 sessions, we achieved an accuracy of about 60%, with subsequent attempts falling between the 40 and 50% range. Since our baseline accuracy wasn't that high, we decided to look at a stronger algorithm that we could use for our predictions. We decided to adapt BrainDA's FPTRCA from the provided lab speller code, since it's known for being quite accurate and stable. FPTRCA, or Filter Bank Task-Related Component Analysis, is designed to learn a model tuned to our specific training data. It applies bandpass filters to our data and uses the parsed data to learn similar patterns within the different trials for each class, creating a different ideal signal for each label. These are called class templates, and during prediction, our model calculates the correlation between these templates and the EEG input, predicting the label with the highest correlation. When we actually applied the algorithm, we saw some interesting results. Initially, we had a training accuracy of 97% for 9 sessions when we ran cross-validation on our FPTRCA model. Our model was probably overfitting to that specific train set, since when we used the model the next day, the accuracy was extremely low in practice, around 20%. Small differences such as hair positioning, electrode placement, and gel differences can cause such inconsistent results. Thus, our FPTRCA algorithm had varying prediction accuracies across days, but it was generally around the 60 to 70% range, which is still higher than our baseline. To summarize, we learned that our FPTRCA algorithm has the potential to work well even without much training data. It works with short stimulus intervals, and the learned patterns are specific to the user, which allow for accurate predictions. When collecting our data, we learned a lot about the strengths and limitations of SSVEPs. Since we only have 8 unique labels, the frequency differences that we selected allowed for highly accurate signal data being collected. With data from around 10 minutes of training, we're able to train an algorithm with high accuracy. SSVP does have limitations though, like how Hansel's eyes would be fatigued after staring at signals for long periods of time, and he also found it difficult to shift focus between the game itself and staring at stimulus squares. Finally, detecting eye blinks was actually simpler than we anticipated. When testing, we found that eye blinks caused significant spikes in EEG amplitude for FP1 and FP2, so we simply needed to set a threshold and record if the absolute amplitude in the signals would cross this threshold consistently. Final step for our process was to map the predicted user actions to actual key presses. Initially, we used PyGUI, but we switched to a reliable keyboard module for our final result. So the main challenges that we faced were the differences in training data across days, causing inconsistent model predictions. We also found it difficult to work with the SVP code initially due to Python version mismatches. Eye blinks were challenging as well, since if Hansel blinked too hard, the headset would be displaced slightly, changing the threshold and stopping detection completely. In the end, we spent roughly 10 hours working in lab sessions to get everything up and running. Let's take a look at our actual gameplay in action. While we weren't able to actually defeat the boss, we landed 1 or 2 hits and dodged some attacks every now and then. As such, our project did work to some extent, since we had some success when it came to controlling our in-game character and performing actions. Again, our biggest challenge was probably with our data collection. Our data collection process was inconsistent across days, and since we weren't experienced in working with the hardware, we likely didn't do the same thing every day. As mentioned in our data collection process, we found that we needed to have a consistent setup to ensure that our SSVP data will be good for classification, and the variability between sessions did lead to our model being inaccurate in some of its predictions. We did find that FBTRCA was a very strong algorithm though, as it outperformed ECCA in our testing. To improve our process, with the limited lab time, we should have allocated some time for recalibration each day, training the model specifically for the cap setup on that day. This would have led to more precise predictions. With more time, we could have implemented a dynamically updating blink detection threshold as well. This way, when the camp was shipped slightly while playing the game, the threshold would update to take into account the current EEG signals from the FP1 and FP2 channels. Our final conclusion is that yes, BCI paradigms are very promising even in the face of tasks with high complexity. Despite our limited time and experience, we still managed to perform multiple actions at once in the gameplay and jump around the boss for a bit. If we incorporated our improvements into the final design, then we could have been more successful. Again, we learned that SSVP is rather limited when it comes to real-time play. Our focus may constantly be shifted between the stimulus and the game, and we might not be able to perform our actions with precise timings. If we were able to incorporate additional BCI systems into our control design, then we probably would have had more success. Let's explore some future extensions that can improve our process.
For future plans with this project, we want to implement a hybrid of SSVP and motor imagery. Eye fatigue was a major issue when doing this project, so a combination of SSVP and MI may improve upon this. It would also improve upon the accuracy, doing both compared to just doing one. For the data collection process, we would need to work on consistency with the headset placement, due to the issues with displacement. This could be through finding a reliable system on putting on the headset, or avoid the subject from moving too much. In addition, acquiring more data would be better to improve the accuracy along with making it generalizable through training on different subjects. Finally, precise movement is the last addition to work on. By altering the SSVP to prioritize certain movements, it will improve upon the accuracy of these keys, which may lead to less critical errors. Plus, more finer movements would be helpful, especially in boss fights. Thank you.